In the last class, we talked about the variational principle and also we talked about the Born-Oppenheimer approximation. Now we will try to appreciate the variational principle further by applying it for the electronic structure calculation in atoms and molecules. So what we have seen that in the variational method you will have to start with a trial function, okay, and then you construct some energy functional like this. I am writing this Hamiltonian, but for the electronic problem, in fact, this would be your electronic Hamiltonian. Okay. So, as I told you that I will explain what exactly do you mean by functional. Only thing you know that this depends on a function. Unlike a function which depends on a number, so it is mapped between one set of numbers to another set of numbers. Here it is a map between a set of functions with another set of numbers. Okay. So that we'll talk about this later. In this case, what you can see, this energy functional Hamiltonian is known because the problem is defined in terms of its Hamiltonian. If you know the problem, you know the Hamiltonian. But what you don't know, the solutions of the corresponding Schrodinger equation. That means you don't know the wave function, you don't know the energy. So in variational principle, as you have seen, that whatever may be your trial function, the corresponding energy calculated using the energy functional with the proper Hamiltonian will never go below the exact ground state energy. So what you can do, you can think about some trial function, calculate the energy functional and check, try to minimize it so that you approach the actual ground state energy. And when your energy approaches the ground state energy, your trial function will approach the exact wave function. So that is the basic principle of using variational principle to make it variational method, approximate method for the quantum chemical calculations. So suppose the way we have learned that whatever function you take can be written always in terms of the linear combination, a set of basis functions. So suppose if you start with a set of basis function, and as I told you, depending on the nature of the problem, you choose the corresponding set of basis functions. Okay. So the basis set, if I get time, I will tell you something related to the basis sets, and you must be knowing, even if you are doing DFT calculations, so there are, say, different functionals, different basis sets, okay, like 6311 plus G double star, etc. These are all basis sets. Like here, your phi i's. So if you have those phi i's, what you do, your trial function, you write it as sum over I Ci phi I. Okay. Now if I substitute it over here, and these are all definite integrals, ultimately what you get, these are the function of these Ci's. Okay. So function of these Ci's. So if you put that over here and then expand, do all integrations, definite integrals, only unknowns are the coefficients, because those functions are your chosen functions, you know. If you integrate them, if you operate Hamiltonian, what would be the corresponding effect? Okay. So your energy functional now is simply a functional of the coefficients. Your job would be to find out those coefficients for which this energy functional becomes minimum. Okay. So the first thing, the simplest possible thing, of course, that del E del Ci equal to 0 for all I. So whatever coefficients are there, you just simply take the derivatives with respect to all coefficients, and as you know that ultimately what you get, you will set up n number of simultaneous linear equations, which you can solve using standard techniques. Numerically also you do construct the corresponding matrix and do the Gaussian elimination sort of numerical technique you adopt, and ultimately you would be able to solve that problem. So in a nutshell, your construction of this, have a trial function, expand the trial function in a given basis set, calculate all these derivatives, get in terms of various CIs, there are n number of CIs unknowns and n number of equations you are getting, like del E del C1 equal to 0, del E del C2 equal to 0, that way n number of such equations you will get, and n number of unknown C1, C2, you solve them, you get it. Once you get them, you put them back over here, because you have already taken an optimal solution. So the corresponding coefficients now they are known, so you know what is the wave function or best possible wave function for this. If you change the basis set, this will change. So the choice of basis set is important, and then ultimately whatever is the best possible combination that you can get through variational principle. Now here, once you know this xi, you just put it over here or in this function, so you know the energy. So what you do when you solve the Schrodinger equation, you get the wave function, you get the energy by doing the variational technique. Instead of solving the Schrodinger equation per se, which is a differential equation, which I am not doing, rather I am converting it to a set of simultaneous linear equations, and that is the procedure what we do. Okay. So today you have supercomputers, you can just simply easily rather diagonalize a trillion by trillion matrix. So if you have 1 trillion say unknowns, you can immediately solve them. Not immediately, depending on which Hamiltonian you are doing, but you would be able to solve them. Okay. So he has come late, so maybe I will repeat. So your steps are application of the variational principle to solve quantum chemical calculations or the electronic structure calculation. You write the trial function as a linear combination of certain known basis functions. Then if you construct the energy functional, it would be simply a function of the coefficients. The functions are chosen by us, so we know what are the other definite integrals. Only thing what we don't know are the coefficients, those coefficients which will give you the best possible solution. For getting that, you construct n number of such equations like I equal to 1, 2 up to n. So what you get is del Ei del Ci equal to 0, n equations, n unknown, solve, you get the wave function, you get the energy. Okay. So we will see some simple textbook level problems of the application. Okay. And these are there in almost all textbooks today. So I will apply this to, let's say, molecular orbital theory. Okay. I will take a very simple example, H2 plus. This is the simplest possible complicated molecule. This is a 1 electron molecule. So you have, let's say, 2 hydrogen nuclei, 2 protons and 1 electron. So if I call R is the distance, and here you have, say, RA, this is the distance we will call RB. Okay. So first we will consider Born-Oppenheimer approximation, separate out electronic mode from the nuclear mode. So we will focus only on that electron. Our job would be to find out the energy and the wave function of that particular electron in H2 plus molecule. Okay. So first we freeze the nuclei. Let's say we know capital R, we have frozen. if we know capital R, immediately we can find out what is RA, what is RB, because RA is the distance of that electron, solitary electron from nucleus A, and RB is the distance of that electron from nucleus B. Okay. So, what about the corresponding electronic Hamiltonian? It would be minus half del square, you have only one electron, minus 1 by RA minus 1 by RB. Okay. So, this is the Hamiltonian. It's pretty simple, isn't it? Now, you see here the trial wave function, here let us say 1SA is the orbital if you have this as the hydrogenic system, and this is 1SB. This is the same 1s orbital of hydrogen centered around nucleus B. So, the simplest possible trial function for this would be C1 1SA plus C2 1SB. Okay. So, this is your candidate for the molecular orbital. A molecular orbital in true sense, because you have only one electron, so the corresponding wave function is so technically is an orbital, and this in a molecule, so this is a molecular orbital. So, what you are having linear combination of two atomic orbitals to construct a molecular orbital. So, this is something what we know as LCAOMO, linear combination of atomic orbitals to construct the molecular orbital. So, here you can see 1SA, I know exactly because I have solved hydrogen atom problem first, 1SB also the same thing, only measured from nucleus B. Only thing what we do not know, C1 and C2. Okay. So, now we construct this energy functional as this xi H electronic written over here. Okay. So, again you can see that if I operate this on 1SA, I can get the corresponding eigenvalues, etc. Similarly, over here only thing C1 and C2, those are the two unknowns. So, if I expand this now, it will be a simple function of C1 and C2. Then if I take del E del C1 equal to 0 and del E del C2 del E del C2 equal to 0, then two equations and two unknowns. There would be two sets of solutions. One would be C1 equal to 1, C2 equal to 1, another would be C1 equal to 1, C2 equal to minus 1, and that also we know. But now, so I can write it as psi now, because these are optimized solutions. After optimization I got the corresponding coefficients, so they are now representative of my wave functions. But these wave functions are nothing but molecular orbitals, remember, because these are wave functions of one electron system and one electron molecule rather. So, this would be your 1SA plus 1SB, this would be your 1SA minus 1SB. Okay. We will see its behavior later. This one we will call bonding orbital, this one we will call anti-bonding molecular orbital. Why that is so, that would be clear in a moment, I will just explain. 1SA plus 1SB, and this is 1SA minus 1SB. Okay. Now, how actually you come to this conclusion now? Instead of doing it in the molecular orbital theory, you can take a simpler route. Now, what is the simpler route? In the Born-Oppenheimer approximation, you have to freeze the nuclei. Suppose I take this R tending to infinity and the electron is here near A. Okay, so I have taken R tending to infinity and you can see RB is much larger than RA if the electron is close to nucleus A. So in the electronic Hamiltonian now is approximately minus half del square minus 1 by RA. Why? Because RB is so large, if I take capital R tending to infinity, 1 by RB is negligible, it's almost like 0. But what is this Hamiltonian? This is hydrogen atom Hamiltonian. And here also you can see, this is nothing but your hydrogen atom. So what is the solution? 1sa, that we have already solved. So, one extreme, I am getting the solution as the 1sa. That means, for this particular condition, RB much greater than RA, in this case, your wave function is approximately, or let's say trial wave function is approximately only 1sa. Okay. Now, if you do the other way around, so it is still R tending to infinity, but now electron is very close to this. So that means your RA is greater than RB, then here you have instead minus 1 by RB, so his xi would be 1sB. So there are two extremes. In this extreme, your C1 is 1, C2 equal to 0. In this extreme, your C1 is 0, C2 is 1. Okay. So your common sense will tell that if the electron is somewhere in between, it is close to both A as well as to B, then the corresponding trial function would be a linear combination of 1sa, 1b. In the limiting case, it would be 1sa, in another limiting case, it would be 1sb. And that is the trial function, what you get. This is your molecular orbital theory, coming from this simple, say, physical or chemical analysis. Okay. Now, what are the natures of these bonding and antibonding molecular orbital? Let's see. Okay. First, so this is your 1sa, this is your 1sb. Okay, so if you see the plots, 1sa behavior is, radial behavior is like this, this 1sb is like this. Okay. Now, if I take 1sa plus 1sb, both are on the positive side. Okay. So, you have to add, like the 1sa is a function at any given point, say this is your R, at any given point, 1sa has a value, 1sb has a value. Let's say I am talking about this point. So you have 1sa here and 1sb here. So the sum would be slightly above. Okay, everywhere you have to add two numbers. So the sum will be slightly higher than the two individual values. Okay. So what it says, if you don't have the electrons over, electrons are distributed, let's say like this. If you don't have the electrons at all, then this nucleus will face this nucleus. So this is your nucleus A, this is your nucleus B. And you know that if you have two, say, same charge particle, they will face Coulomb repulsion. And if you try to make a bond, bring them closer, they will face tremendous repulsion and they will go away. So bond will not be formed, or the molecule will not be formed from the atoms. Okay. So how do you do it? Now you put, so this is something what I call electron glue. So if you put electrons are negatively charged, so it will attract the nucleus towards this side, it will attract towards the nucleus side. It is like a cream biscuit. So you have some cream inside, two biscuits are getting coupled. Okay. And this is actually, this interplay of electron-nuclear attraction is attractive, nuclear-nuclear repulsion, they are repulsive. So interplay of electron-electron repulsion also is there, but that's much smaller in quantity, in magnitude. Then the resultant, if it is attractive, they will attract each other. Okay. And we call this as the bond formation. So there would be bond formation. Now, here you can see, this is what we could find out, that you have more electron density in between the two nuclei, or what we call accumulation of electron density. Okay, you have accumulation of electron density in between the nuclei. Okay. So if you have accumulation of electron density, obviously it is going to a much better situation as far as bonding is concerned than if you keep them in the individual atomic orbitals. That means if I call this, say this is the energy level of 1sa and this is the energy level of 1sb, for this particular orbital, the energy level will be down, because you have additional this much. So if I call the area under this curve, so here you can see it is more than if you would have been only in this atomic orbital. So if you have separate atomic orbitals, in this case electron-nuclear attraction is more and that is negative, so the energy will go down. Okay. So energy goes down, and because it gives you bonding, we'll call this molecular orbital as the bonding molecular orbital. So bonding molecular orbital, how will you designate? Because this one is originating from 1s orbital, so I will put 1s. Then molecular orbitals, you know how atomic orbitals are defined? Who would be able to tell? How do you define 1s, let's say 2s, 2p, s orbital, p orbital, d orbital? How do you define? How will you call that this is a p orbital? What is the definition? Tell. Doing research in quantum chemistry, you tell. How do you define? The school level problem. Tell. How do you define a p orbital or d orbital? How? How do you differentiate between these two? What? Shape of the lobe. No. This is this orbital angular momentum quantum number 0, 1, 2, etc. We call it S, we call it P, we call it D, we call it F, and so on. Did you know this? No. No or yes? So why didn't you tell? That is the exact quantum mechanical definition of the orbital. Don't forget. No shape, nothing. Shape comes later on. First you define the orbital. This is the definition. Perfect. Now, in case of molecules, again you get the orbitals if there is a one electron molecule. Later on we will see what we do with that. So in that case, what you do, you talk about ml values or mod ml values instead of L. L is not a good quantum number. In order that L should be a good quantum number, the potential should be spherically symmetric, which is true for atoms. Okay, because it has a central potential. The electronuclear potential energy doesn't depend on, say, the angular variables. Of course, you have to remember one electron problem. But in case of molecules, the simplest possible, most symmetric molecule is a linear molecule, which is having axial symmetry. For one electron molecule, let's say H2 plus will have a cylindrical symmetry. So there L is not a good quantum number, but the component of L, let's say along the internuclear axis, if you take that to Z axis, that is your ml value. Now ml is also quantized, but L you don't know, because L is not a good quantum number anymore. Okay, because it has lost its symmetry. So ml values, if you have 0, 1, 2, 3, etc., you call it sigma orbital, you call it pi. So these are the Latin components, delta, phi, and so on. You see, S becomes sigma, P becomes pi, D becomes delta, F becomes phi. They are called molecular orbitals. Sigma orbital, pi orbital, delta orbital, phi orbital. And 0, only one number. So all sigma orbitals are non-degenerate. Pi, you can see it can be plus 1 or minus 1. So there would be two pi orbitals, one above the plane, one below the plane. Pi orbital is doubly degenerate. Okay. Delta is doubly degenerate. Phi is doubly degenerate. That is the structure of the molecular orbital. Okay. So I will call this as 1s sigma. Why sigma? Here total L is 0 plus 0, means 0. What should be its component? 0 can have only component 0. If it is a p orbital, L is 1, so its component can be 1, 0, minus 1. You get 3 pi orbitals also, px, py, pz. If you just simply take the linear combination of p1, p0 and p minus 1, you will get them. Because ml values can be 1, 0 and minus 1. Okay, but for S, 0 means component is also 0. So you get only sigma. And because of the symmetry, you can see the symmetry is, it is symmetric with respect to this. So we call this as the, of the G character. We will call this orbital as the 1s sigma G. Okay. So you get, if I have one electron problem and this goes to this place, this is the 1s sigma G orbital, where you can see that your molecule would prefer to send its electron not in either of the atomic orbitals, rather it would prefer to go to the molecular orbital, bonding molecular orbital, remember. Okay. Which is lower in energy. Perfect. What about the other one? But before that, let me tell you why bonding molecular orbital is bonding. You see, now, so this one is atomic orbital, this one is atomic orbital, but these broken lines, they are giving you your 1s sigma G. So that is the structure of 1s sigma G. Okay. But now you can see that all these orbitals, they are normalized. So normalized means what? The area under the curve must be 1. So previously, suppose if I would have taken all this 1SA plus 1SB, like this one and this one separately, that was the area under the curve. But now my area under the curve is like this, where there is a bulge in between the two nuclei, because there is an accumulation of electron density. This is only point you will see in your textbooks, at least most of the textbooks. But now you can see there is another way of looking into it, because the area under the curve should be conserved and there is some extra component in between the nuclei. There must be some reduction over here. Some reduction over here, that means it will go like this, and some reduction over here, that means it will go like this. Okay, away from the nucleus, there would be depletion of electron density. In between the nuclei, there would be accumulation of density. Is it clear? Because the area under the curve should be same in case of atom versus in case of molecular orbitals. Okay. What is the physical meaning or chemical meaning of this? You can see we are trying to understand the chemical bonding, nature of chemical bonding. Okay, how chemical bonds are formed. This is the exact quantum mechanical way of doing it, but within a molecular orbital theory framework. Do you understand? So now here you can see that if you put extra electron density over here, that is beneficial for the bonding situation or the molecule formation. But if you put some extra electron density here or here, that is detrimental. Because your electron density now will simply attract the nuclei, that will break the bond. So you can see when the electron is going to the molecular orbital without staying in atomic orbitals, it is basically stabilizing the molecule formation in two different ways. One, through the accumulation of electron density in between the nuclei or internuclear space, wherever, and depletion of electron density away from the nucleus. Two ways it is facilitating the molecule formation. Perfect? Did you understand the second point also? So you have depletion of electron density away from this. But if you, let's say, subtract this, you go to this, if you subtract this, everywhere it should be less than this curve, below atomic orbital curve. That means you will get picture would be like this. At some point, there would be 0, isn't it? And this is what we call node, where the wave function molecular orbital has the value 0. So this side you have positive, this side you have negative. So this is a node. In general, for any system, if the number of nodes increases, the energy increases. So that means here, previously you had 0 node, now you have 1 node, that means it would be of higher energy. And in this case, here you can see that it will reduce the electron density in between the nuclei. So that means now nuclei will have more face-to-face interaction rather than in atomic orbitals. So it would destabilize in comparison to the atomic case. And the second point also, because here is a depletion, if you want to see that your area under the curve should be same, there would be accumulation here, accumulation here. That will take it away. That means in two ways, antibonding is antibonding, and in two ways, bonding is bonding. Okay? And here you can see the symmetries of U symmetry. Plus goes to minus if you do the corresponding I operation. Okay? So in this case, we will call this as 1 is sigma U. Again sigma, because you have only combination of 0 and 0 will give you 0, and it has a say component ml should be 0 only. Okay? And this one will call antibonding orbital, and antibonding orbital will have, and as it is of higher energy, we put a star. So star will tell you that two different types of 1s sigma orbitals, one is of lower energy, one is of higher energy. Okay? So this is your 1s sigma, but remember, this is when we are solving without considering, so the typical bond length would be optimum or the equilibrium bond length. Then only you get this scenario. So it is not always true that bonding orbitals always will give you advantage. Because if you squeeze, suppose it is undergoing, say, vibrational motion, and at points it can come very close to each other. When they come very close to each other, nuclear repulsion will dominate. Even that extra electronuclear attraction will not be able to do anything. So if you do this at different capital R, if you do it, you can generate potential energy surface. For if I go for hydrogen, let's say molecule, then hydrogen molecule will write this as 1s sigma g 2. This is the molecular electronic configuration where we assume again that the electrons are not interacting with each other. So I give 1s sigma g to electron 1, 1s sigma g to electron 2, as we did 1s2 2s2. Here we can do 1s sigma g 2, 2s sigma g 2, 2p pi x 1, pi y 1, etc. So that we can do. Okay, and these are what we will call ground state molecular electronic configuration. Okay, so molecular electronic configuration, as again this doesn't give you proper physical behavior, because electrons are actually interacting, and if you consider electron-electron repulsion, obviously this beautiful picture of having beautiful symmetry will be lost. Okay. Now if I want to check as a function of R how these energies, what we could see over here, beautiful picture. So this one is only at the equilibrium. So if I plot it, let's say for hydrogen molecule, so what I get, so this is my potential energy, this is capital R. So this is your 1s sigma g, this is your 1s sigma u star. So this is the energy with respect to two energy of hydrogen atoms. Okay. So that means if you put two electrons in atomic orbitals, this is the energy, and relative to that energy level, what is happening when the bond is getting formed. So when R is pretty large, that means two hydrogen atoms are more or less two atoms. So there is hardly any difference. They are very close to each other. But after that you can see that repulsion is increasing, and ultimately when they are very close, the two nuclei are very close, then the repulsion is shoot up. Here also you can just go here, nuclear repulsion is increasing, but electronuclear attraction is also increasing, so energy is going down. Ultimately at a point it will come that all repulsive, attractive, they will cancel each other. You will reach the equilibrium point, and this is the point which we will call equilibrium bond length of, let's say, hydrogen atom. And here, the previous plot what I had shown, you can see that relative to this energy is down, but this energy is up. So this is your 1s sigma u star energy, this is your 1s sigma g energy. But not everywhere this is true. But now what will happen? Suppose if I call this is my hydrogen atom A, this is my hydrogen atom B. They are far off. So there is hardly any interaction. So its energy is same as the energy of these two. But ultimately, when we will keep on bringing then you can see some extra electron density is coming in between the nuclei. That means electron nuclear attraction is increasing in between the nuclei, and accordingly it goes down. But here electron nuclear attraction is increasing somewhere else, so the energy will go up. Okay, and here there would be balance. But after that, if you squeeze, then you can see two nuclei will come, let's say, over here. So they will be squeezed that much. The capital R is so small that the two nuclei are creating lots of nuclear repulsion, which cannot be compensated by electronuclear attraction, and it goes up. So even if it is in bonding orbital, if your bond length is too small, the energy will go up. Okay, so it is not that if it is bonding, always it will be stable. No, you can see. You have to consider the vibrating molecule and what type of vibration it is going on. Then the energy variation would be in this fashion. How do you write? Let's say this one, the corresponding wave function. This is the electronic configuration anyway. How do you write the wave function? Let's see. You have, let's say, phi 1 as 1s sigma g into alpha, phi 2 as 1s sigma g into beta. So this is your 1s sigma g 2. One is in 1s sigma g alpha, other according to Pauli exclusion principle, one would be alpha, another would be beta. Then your psi 1 2 would be 1 by root 2, phi 1 1, phi 1 2, phi 2 1, phi 2 2, and you know that this is the Slater determinant. So the simplest possible way of writing the corresponding wave function of the hydrogen molecule from, let's say, the ground state electronic configuration is construct the spin orbitals, then construct your Slater determinant. That would be a valid wave function. In fact, as we will see that this is exact wave function within Hartree-Fock theory. So we will tell maybe after the break something about the Hartree-Fock theory. Okay. Now suppose there is another important and popular electronic structure method. One is molecular orbital theory, other is valence bond theory. Okay. That means there we talk about the bonds, valence bond theory. There your trial function is written as C1, 1SA1, 1SB2 plus C2, 1SA2, 1SB1. So here you can see instead of taking individual orbitals, you are taking a bond. So this is the representative of a bond. A is giving one electron, B is giving another electron. So a bond is represented like this. But as electrons are indistinguishable, you have to have 1sa2 and 1s. Now if you put this, create energy functional, take the derivatives with respect to C1 and C2 to be 0, two equations, two unknowns, then you get C1 equal to 1, C2 equal to 1 and C1 equal to 1, C2 equal to minus 1. So two different valence bond wave functions you will get, and this one will have lower energy than in atomic orbital, and this one will have higher energy than in atomic orbital. So exactly the same way, but the wave functions are now different because your trial function was different. One from MO theory, one from VB theory. But if you take different trial functions, you will get different. But in general, as I told you, you write it like this. And sometimes you can do it this also. Your xi is, let's say, sum over I Ci e to the power minus alpha I x or x square. If they are x, they are Slater orbitals. If x square, they are Gaussian orbitals. Okay. So if you do this, and then I call E del Ci equal to 0 for all I, and also del E del alpha I equal to 0 for all I. That means you now have 2n sets of unknowns and 2n sets of equations you can solve. So you get more flexibility in your optimization problem. Okay. So when you do actual calculation, there are such variational parameters here and there, and you can optimize all of them. Okay. In fact, one is that improve the orbitals, that we will see within Hartree-Fock theory and so on. And of course, as I told you, that you write it in the form of the determinant, that is the exact wave function for the Hartree-Fock theory. Now what will you do as far as the improvement of those determinantal wave functions are concerned? That I will tell little bit about the post-Hartree-Fock theories or correlated theories. Later on, I will tell one of them elaborately, that is the density functional theory. So I think at this point I stop, and after that I will go for the Hartree-Fock theory, all self-persistent field techniques. Molecules, how to get the wave functions also, let's say in the form of the Slater determinant. But the major problem with the orbitals is that they are all one electron functions. So we are trying to express a many electron system, many electron atom or a many electron molecule in terms of one electron functions. Okay. So obviously that is not the real picture, because we are not considering electron-electron repulsion. Okay. So whatever description we are giving, even when we construct, let's say, the Slater determinant, unless we modify the orbitals, that will also give me the same problem as the independent electron system. So let's see the source of the problem. How do you write? And I am now talking mainly about the electronic problem, because I know the within Born-Oppenheimer approximation, first we freeze the nuclei and then we solve the electronic Schrodinger equation, get electronic energy, add with the nuclear repulsion, construct the potential energy for the nuclei, and solve nuclear problem, and then go back iteratively, you solve the electronic structure problem. Okay. Now in this case, so the Hamiltonian is a minus half sum over I del I square minus Z by Ri plus half Ij, I not equal to j, 1 by Rij. So this is your many electron atom Hamiltonian. So this is sum over I Z by Ri. So if you have many electrons, only one nucleus, because it's an atomic case. So here this is the electronic kinetic energy, electron nuclear attraction, electron repulsion. This is the double summation, and this hash means I not equal to j. So because I don't want to get R11, R22, those terms are not required, that's why this has half. Why? Because you get R12 and also R21, so that double counting error, to minimize, I have put half factor. Okay, so this is a general electronic Hamiltonian for a many electron atom. In case of molecule, there is nothing difficulty. This one, you simply write minus sum over alpha, sum over I, z alpha by r I alpha. So this is for the molecules. So in case of molecules, that will be only difference. So alpha is the index of the nuclei, I is the index of the electrons. Okay, and Ri alpha means capital R alpha minus small ri mod. That is your Ri alpha. That means, sorry, I alpha. So this Ri alpha is your R alpha minus Ri. So this is your distance between the nucleus to alpha nucleus to the ith electron. Okay, and sum over all such distances, that will give you the molecular electronic Hamiltonian. Okay, but if you take this Hamiltonian, so your time independent Schrodinger equation is H electronic, psi electronic, E electronic, psi electronic. This is analytically not solvable. So you have to solve it numerically. For one electron problem, you can solve it. But for many electron problem, you cannot solve analytically. So you have to solve it numerically. So I will tell you, say, one of the most popular methods, so that you can incorporate electron-electron repulsion within the orbitals. Still, you see, not necessarily you should be there in the orbital picture, but the chemists prefer to talk about orbitals. Why? Because orbitals are three-dimensional stuff, one electron function. So you can visualize orbitals, you can draw pictures, you can have chemical models, talk about reaction mechanisms very easily. But if you have to talk about the wave functions, obviously you won't be able to do this, because that's in a much higher dimension. So these are called SCF methods or self-consistent field methods. Self-consistent field, the general meaning is you start with some trial stuff, keep on improving upon in an iterative fashion, and you go until your required, say, tolerance limit is attained. Okay, so this is your self-consistent field method. So here, what is your main aim of doing this? You are trying to incorporate electron-electron repulsion into the orbital picture. Okay. So I will tell you, let's say, Hartree-Fock theory. I will first tell you the general stuff so that qualitatively you can understand. Suppose if you have an atom, neon atom, 1s2, 2s2, 2p6. Here each electron is attached to, let's say, one orbital. So if you solve this, you get like minus half del minus z by r2p psi 2p. So you can see this is like hydrogenic system. So if you want to get the 2p orbital, these are hydrogenic orbitals. Okay, these are hydrogenic orbitals. So that means they are the solutions of hydrogen like Schrodinger equation. You see, I am focusing only on one electron over here, not other electrons. So once I write this one, basically I am solving similar equations for 1s, 2s, 2p. All one electron problems. You don't see one important thing, that is electron-electron repulsion, which is missing, totally missing. You remember when I wrote the electronic Hamiltonian, electron-electron repulsion term was there, which is not there. So when you go for the orbital picture or the electronic configuration, the way we write, that particular important term is missing completely. So what Hartree-Fock theory they had shown, that you do it like this. This one, let's say if I call the core Hamiltonian, this is what we call the core Hamiltonian. So if I have the core Hamiltonian, let's say for 2p, is this one, core Hamiltonian for 2p, plus 2p electron-electron repulsion with other electrons, minus exchange interactions. This is operating on, let's say, psi 2p tilde, e 2p tilde, psi 2p tilde. That means what you are doing, how you calculate that prescription will come from Hartree-Fock theory. Once you get this solved, you get psi 2p, still orbital because one electron problem. But this orbital is much better than the hydrogenic orbitals because it contains electron-electron repulsion and also the exchange. To start with, you can start with hydrogenic, calculate this one, this one, this one, do it once, get a new set of size. With the new set of size, you calculate these two, again solve, keep on doing it until the two successive iterations, they will give, for all practical purposes, same result. Then we call that it has reached self-consistence. Okay, or the calculation has converged. Do you understand? So in computation, you exactly do the same thing when you go for the self-consistent calculation. So now question is how you calculate these electron-electron repulsion and exchange. That was given by Hartree-Fock theory. But to appreciate Hartree-Fock theory, and I just explained what is called self-consistent method also. Okay, that iterative technique is called, because they will depend on the orbitals, all orbitals. You start with all hydrogenic orbitals, calculate this, get this one, then you get all better quality orbitals, put them over there and keep on doing it until two successive iterations will give you the same result. Okay, that means you have reached the self-consistence. Now, how to calculate those interactions, electron-electron interaction and exchange interaction? So we will see. So the original idea came from Hartree, D.R. Hartree, and then actually Fock, V.A. Fock of Russian origin, he had shown some anomaly in Hartree's theory, so he put some extra correction term, that is the exchange term, and then you get better quality orbitals. Okay, there are certain problems with Hartree-Fock theory also, but these orbitals, Hartree-Fock orbitals, are way better than your original hydrogenic orbitals, because it contains maybe in the average way some electron-electron repulsion. Okay, so let's see how Hartree did it. Hartree method or Hartree theory. Okay. So Hartree had shown that to start with hydrogenic orbitals, they are known to you, 1s, 2s, 2p. You have solved hydrogen atom problem and you know all of them. Actually hydrogenic system, Z is also coming into the picture. So this is the product wave function. So he had used simple possible knowledge that the joint probability would be product of the two probabilities. That means your total wave function of n electrons would be product of individual electronic wave functions, or in this case individual orbitals. Okay, that means psi 1, 2 up to n, he has considered approximately this as phi 1 like r1, theta 1, phi 1 into phi 2, which is r2, theta 2, phi 2 up to phi n, rn, theta n, phi n. In fact, actually this is not the case. These are not the orbitals. You know that each orbital, that is what we call today, we know that's called restricted Hartree-Fock theory or RHF theory. Okay. So in this case, your original electronic configuration, you remember 1s2, that means two electrons are attached to 1s orbital, one with alpha spin, one with the beta spin. That means two different spin orbitals, but orbitals are same for two electrons. That means this one is basically xi1 into xi2 into xi n. Okay. So that means what it is? So phi 1 alpha into phi 1 beta up to phi n beta. So that means phi n by 2 beta, isn't it? So altogether you need n by 2 number of orbitals, but this is only for closed cell systems. You get the restricted Hartree-Fock theory. Okay. So you see, when I write 1s2, 1s orbital coming once, 1s orbital coming twice, one with the alpha spin, another with the beta spin. When I solve the equation, spin is not taken care of. Spin we put it by hand at the end. So how many will you have? Each one 2. So altogether if you have n electrons, there would be n by 2 orbitals only, isn't it? You see, when I write neon atom, there are 10 electrons. 1s, 1 orbital, 2s, 1 orbital, 2p, 3 orbitals. Total 5 orbitals only, isn't it? Each one have 1 alpha spin, 1 beta spin. So number of orbitals would be n by 2. So you have to get n by 2 only number of orbitals. So how do you do it? Let's see. So your job would be, Hartree had shown that how you can get the electron-electron repulsion and how you can improve upon this in a cell-consistent fashion. So that we will see. And another thing is the probability density of, let's say, jth electron is rho j, and this is just phi j mod square. So the probability density of electron 1 is phi 1 mod square, this way, or to be precise, probability density associated with orbital 1 is phi 1 mod square, phi 2 mod square, etc., up to phi n by 2 mod square. Now, to focus your attention to electron 1, let us say there are n electrons. You focus your attention to electron 1. Okay. Electron 1 is interacting with electron 2, let us say. So what is electron-electron repulsion then? V12 electron-electron. If we consider both of them point charges, for point charges Q1, Q2 by R12, where Q1 is charge of one electron 1, charge of electron 2 by R12. So in atomic unit 1 by 4 pi epsilon 0 unit, it is just 1 by 4 pi epsilon 0 unit. Okay, 1 by R12, if they are considered point charges. Now suppose electron 1 is interacting with a smeared out charge distribution. So a smeared out charge distribution of electron 2, then it should be, your V12 would be Q1 integral rho j by R12 rho j would be multiplied by electronic charge d tau 2 rho 2. Okay. So that is the charge distribution probability density, and if you put a charge, it would be rho 2 by this. So one electronic charge from there and one electronic charge here, I will take it out. That means this becomes integral phi 2 mod square by R12 d tau 2. Okay, so if you want to calculate the electron-electron repulsion, electron 1 and electron 2 is a smeared out charge. I can start with my original phi 2 orbital, that hydrogenic orbital I had started with. I can immediately calculate phi 2 mod square by R12, integrate. I get a number. V12 electron-electron repulsion is now just a number. Okay. So now similarly, suppose V13 would be integral phi 3 mod square by R13 d tau 3. Electron 1 interacting with electron 3, and that way 1, 3, 1, 4 up to 1 n. So net electron-electron repulsion, say R1, theta 1, phi 1, okay. This is what? This is your V12 plus V13 plus up to V1n. isn't it? Here you can say R1j is there, that means R1 minus Rj. I am integrating over d tau j, so all j containing part is integrated out. It is dependent, it will depend only on the coordinates of electron 1. That's why I have put R1 theta 1 phi 1. Okay. Now what is the net potential felt by electron 1? That means if I call this as the V1, net potential felt by electron 1, R1 theta 1 phi 1, this would be this V1 EE minus Z by R1. That is the net potential. This total electron-electron repulsion minus electronuclear attraction. Okay, now you see your original phi 1 orbital. It was the solution of minus half del 1 square minus Z by R1 phi 1 is E1 phi 1. Okay, that was your original solution, where there is no electron-electron repulsion, but that was your hydrogenic orbital is coming as the solution of that one. But now Hartree has given the prescription minus half del 1 square minus Z by R1 plus something. But you see that if you want to get this orbital picture, you won't get, because it has still theta and phi dependence. So Hartree had applied a very clever trick, that you consider that the electrons are smeared out, all of them, but they would try to be in such a way distributed that overall electron distribution would be spherical in nature. So you have a spherical symmetry of the electron density distribution, and that is what is called central field approximation. Central, I told you, where there is dependence only on R but not on theta and phi. So this is what we call central field approximation. So if you do the central field approximation, it would be V1 R1, this is 0 to 2 pi, 0 to pi, V1 R1 theta 1 phi 1 sin theta 1 d theta 1 d phi 1. This is just the volume element, the angular part, 0 to 2 pi, 0 to pi, sin theta 1, d theta 1, d phi 1. So if you integrate over theta and phi with the spherical limits 0 to 2 pi and 0 to pi, this would be just a function of R1. So this is central now, so that you have legitimate right to get the orbitals now, which we will call Hartree orbitals. But now wait, we have to wait for a while. So I add this and I call this, let's say, as T1 1 as E1 tilde T1 1. So now if I solve, I am not getting phi 1. It's not my hydrogenic orbital anymore. I get a kind of Hartree orbital where in some way spherical average smeared out electron density distribution for all other electrons other than electron 1. I have introduced electron-electron repulsion now. So it is way better than my original hydrogenic orbitals. Okay. But what about the other electrons? Now, Now focus on electron 2 now. Electron 2. So that means what? I will get V21, V23 up to V2n. Isn't it? How do you get it? The electron part? You interact with minus T1 mod square plus phi 3 mod square plus up to phi n mod square. So your electron 2 is interacting with this charge distribution, isn't it? Only difference is that for electron 1 I have considered this improved orbital, not my original hydrogenic orbital. Then I take all these steps, I construct the total potential, do central field approximation, and then I get the equation like this. Equation would be like minus half del 2 square minus z by R2 plus V2 R2. This would be T2 2 E2. This is equal to E2 tilde T2 2. Okay. Do you follow? So I get a better quality orbital for electron 2 also. Now I do the same exercise up to electron n. So I get T1 1, T2 2 up to Tn n. Okay. Then what shall I do? Again I will focus my attention to electron 1. And there I calculate all such orbitals. You go back to the original one. You again focus on electron 1. And for electron 1, you keep everything like T2 to Tn. You do all these steps, you get a better one. So if I call them like this, say T1 n, T2 n, or if I call them as T1 0, T2 0 up to Tn 0, then next step you get T1 1, T2 1 up to Tn 1, then I get T1 2, T2 2 up to Tn 2. That means this is the first stage of iteration, second stage of iteration, third stage of iteration, and so on. You keep on improving via self-consistent field technique. Do you understand? You do it, you set your self-consistent field limit, that suppose if I call Ej n plus 1 minus Ej n mod by Ej n plus 1 less than equal to some delta. Is whatever, 10 to the minus 5, minus 6, minus 10, minus 12, depending on your requirement and your computer power, you make it as small as possible. That means for all j, remember this should be for all j. So all the orbitals, you are getting not only the improved orbitals, you are getting improved energy also. Molecular orbital energies also, or atomic orbital energies also you are getting, isn't it? Now for all orbitals, if two successive stages of iteration, when you will see that all energy levels are within my tolerance limit, that means there is, as far as I am concerned, there is no change in the corresponding energy values in two successive iterations. I will write a program that stop. I have reached my self-consistency, or I have converged results. So now I get all the improved Hartree orbitals, self-consistent field Hartree orbitals. The wave function would be then product of all these orbitals. Okay. or n by 2 number of such orbitals, I get the corresponding product. So individually I multiply with alpha, beta and get spin orbitals, and I get in the form of a product. So Hartree wave function is the product wave function. Now the question comes, what is the total energy of the, here I am talking about only molecular orbital energies, individual electron energies. Whatever the total one. So total one, so Hartree's psi 1, 2 up to n, it would be, say, if I call that let's say G1 1, G2 2, here G1 is same as G2, okay, that way I will go up to Gn. So what are these G's? They are SCF orbitals, like that n plus 1 stage where this is satisfied, I call, let's say, them as the G orbitals. They are self consistent field Hartree orbitals. But Hartree's wave function is the product wave function, remember. Okay, so I have solved my problem as far as Hartree method is concerned. But suppose I have to now get the total energy of the molecule, total electronic energy. How do you get? So first thing what you can see, that total energy is never sum over I EI. If I call that electron 1 has U1 energy, electron 2 has E2 energy, so if I add all of them I will get the total electronic energy. No. Why? Because you remember the way we calculated, at the first stage I calculated 1 interacting with 2. In the second stage I calculated 2 interacting with 1. So there is a double counting. So I have to remove that double counting error. So how do you remove that double counting error? That means it should be minus half Ij Jij. So this Jij is called Coulomb integral. We will talk about Coulomb operator also, which is associated to this, and this one is sum over I, so E becomes sum over I EI minus half Ij Gi I mod square Gj it is just the Coulomb integral. You can see a simple your rho I rho j by Rij. Okay, only thing I should not be j and Ij say the I should not be j and Ij and Ji should be different. That's why you have half factor, and that we have already explained. So now we have learned how to calculate the total energy also. You have to subtract, and this one, because this is we have calculated twice. Okay, so we have subtracted the half of that. So, but now here you can see the Fock noticed one important thing, that Hartree's overall treatment is very good, that it can tackle electron-electron repulsion in an average fashion, and it would give a much improved orbitals as far as the electron-electron repulsions are concerned. But you think about Pauli's antisymmetry principle, that is very, very important. If you interchange the coordinates of I and j, it will be a totally new function. You know that for bosons it should be symmetric, that means that same function multiplied by +1. If it is case of fermions like electrons, it should be antisymmetric, that is called Pauli's antisymmetry principle. That means the wave function must change its sign, not the total wave function is going to get changed. Here the Hartree method or Hartree's product wave function doesn't satisfy Pauli's antisymmetry principle. So he had given certain corrections. Let's wait till tomorrow. I will tell you what were the corrections. So he had to bring in exchange into the picture. Okay. So I will tell you in the next class.